Great, so we have covered a bunch of material regarding LDPC codes now, and now we're looking at the final bits and pieces that we need in order to implement LDPC codes. Finally, and we're looking at some related code constructions in this chapter as well. So the first thing we're looking at is the encoding of LDPC codes. So this is an aspect that we have missed so far, so we didn't really look at encoding. And this is something we're going to do in this video. So let's talk a little bit about encoding LDPC codes. So in general, an LDPC code is nothing else as a block code. An LDPC code can be treated as any other block code when it comes to encoding. So we have a parity check matrix. From the parity check matrix, we can get a generator matrix. We know the generator matrix must be orthogonal to H, so we can find a generator matrix that multiplies H transpose and leads to 0. And we saw in the second chapter that if H has this very particular structure, so it has a matrix P transposed, and then next to it we have an identity matrix of size n times k, then the generator matrix is just the identity matrix of size k times k, followed by this matrix P. Very simple. And we saw how we can generate or how we can transform the parity check matrix such that it has this specific form. So for instance, we can swap columns, we can swap rows, and we can also replace a row by the linear combination of other rows. So at the end of the day, we could use Gauss-Jordan elimination, and using Gauss-Jordan elimination, we can transform H to matrix P transposed, followed by a matrix I n minus k times n minus k. And then we have this matrix, we can get the generator matrix G, and then we just obtain the code words by multiplying our information word with the generator matrix. That would be the standard way. However, that's usually not feasible. So the issue here is that obtaining the generator matrix G is in general a rather complex process. So the generator matrix G will most likely not be sparse. So because we need to do Gauss-Jordan elimination, which means, especially if we have a regular code, we don't have columns with a single one. So we need to get rid of ones, which means we need to add some rows and replace the other rows. So this will introduce new ones, and we need to get rid of those. So it means that this matrix P transpose will, with a very, very high probability, not be sparse. And hence, coding requirements and the complexity requirements and the storage requirements, they will scale with n squared. So this is not so nice because storing the generator matrix, storing a big matrix will be pretty bad and pretty difficult. So we need to find easier ways of storing the matrix. So there is fortunately a workaround. And the idea is that instead of finding a generator matrix, we try to encode using H directly. So we can encode using H directly. How do we do this? Well, we follow a certain procedure. And the first thing we do is we transform H into what we call an upper triangular form or approximate upper triangular form. So what does it mean? It means that only using row and column permutations, so we do row and column permutations, we transform the matrix H into a matrix H prime. This matrix H prime has this form. So it has, we decompose it into 6 submatrices. The most important one is the submatrix T. The submatrix T is a matrix, let me put it here at the top, submatrix T is a matrix that has a lower triangular form. It looks like this. And I just saw a typo. This should be approximate lower triangular form. Essentially, you can also put in lower triangular upper form. Both methods exist. Here we just stick to the lower form. It's a matter of definition how you want to proceed it. So this matrix T has entries only on the main diagonal or below. And it has 0 everywhere else. So it has 0 on the upper right part above the main diagonal. We have a lot of zeros here. And on the main diagonal and below, we have possible non-zero entries. The size of this matrix is the square matrix as of size m minus g times m minus g. Of course, we cannot get it into full lower triangular form because we have regular code, and here we would need to have one single row that has just one single column. The last one must be only have a single one. In a regular code, such a thing doesn't exist. So there is always some rows that don't fit into this, and this is what we put in the so-called gap. So we have this lower triangular form over here. That's the matrix T. And everything that doesn't fit into this, we put below. So we put the matrix E below. The matrix E is of size M, the size of this matrix. E is of size G times M minus G. Then, so here we have M minus G rows and G rows below. Here we have M minus G columns. And here we have subdivide the matrix so that we have G columns over here. And here we have K columns. So the first K columns, they correspond to the information bits of the code. Then we have G columns, and then we have M minus G further columns. And what G is what we call the gap of this approximate representation. We'll see that the encoding complexity depends on G, and if G becomes smaller, the encoding complexity becomes smaller. And if these row and column permutations transform H into H prime are well chosen, then we can have a very, very small such gap. Okay, so now how can we do the encoding? So the next step we do is we eliminate E. So we have this matrix E down here, and we don't want this matrix E. We want to get rid of this matrix E. How can we get rid of this matrix E? Well, that's simple, because here we have a lower triangular form. So we can use Gauss-Jordan elimination to clear E. So we can just clear E by adding some rows and columns from E. So for instance, we have a single entry in this row, in this first column. So for instance, if we want to get rid of these entries, we just multiply the rows by this entry, then we get rid of the first column, and so on. So using operations, Gauss-Jordan elimination, we can get rid of E. And we have an equivalent parity-check matrix. This is important. Parity-check matrix doesn't change. It's going to be equivalent because it's an operation that is allowed to be performed for generating equivalent parity-check matrix, according to chapter 2. So let's take a look. Let's do this. You can do this by hand. we can also do this by just multiplying the matrix by this guy. So identity matrix, and we have zero matrix here, and minus e times t to the power minus 1. So why is there a minus? We are using binary numbers, so that's where we can put a plus. Just put the minus to have it a little bit more visual. So this is so-called Schur complement, first matrix that's equivalent to Gauss-Jordan elimination. So let's take a look at an example why this works. We look at the identity matrix, we have zero matrix, we have minus e times e to the power minus 1. I'm just going to spread this a little bit more, times t minus 1. And we have a matrix. I'm just going to put the left part of this, so matrix B, T, D, E. So now the matrix multiplication works by taking the first row of this matrix and multiplying with the different columns of the right-hand side. It's the identity matrix times B plus 0 times D. So this is just equal to B. That essentially leaves the first row unchanged. So then we have the identity matrix. Come on, here we go. The identity matrix times T plus 0 times E. That just leaves us with T. We use a little bit more space because we need the space for the second. So now what we have is the following. So we have minus e times t to power minus 1 plus b times b plus the identity matrix times b. Okay, so this is minus e t to power minus 1 times b plus d. Okay, we have to live with that one. And then we have minus e times t to the power minus 1 times t plus the identity matrix times e. So this is minus e times t to the power minus 1 times t plus e times the identity matrix, which is e. And t to the power minus 1 times t. This is just equal to the identity matrix. So we have minus e plus e, that's just going to be 0. Or plus e plus e in the field of binary numbers, it's going to be 0. So when you do this with the extended matrix with A, C, B, D, T, E, and you multiply it with this Schur complement, you get H tilde, and you end up with the first row being unchanged, so A, B, T, and the second row being C tilde, D tilde, and the zero matrix, which is this guy. And D tilde is the one that we just calculated, so it's minus E t to the power minus 1 times B plus D. And C tilde is minus ET minus 1 times A plus C. And as I said, we can all instances of minus into a plus, as we are exclusively working with binary numbers over here. Okay, so now we have this matrix H tilde, which is again an equivalent parity check matrix of our code. It describes exactly the same code. Okay, so now how can we do the encoding? So we divide our code word into 3 parts, and each part corresponds to one of those submatrices in H tilde. So U is our information word, that's the message, it's K bits. P1 are the first G parity bits. So P1 are the first G parity bits, and P2 are the remaining parity bits. So that means we can now obtain P1 and P2 from H tilde. How can we do this? So what we can do is the following. So we can say that X is equal to U, P1 and P2. And what we know is that H times X transposed must be equal to 0. And this is equivalent to saying that H tilde times X transposed is equal to 0, because we describe the same code. So we can write this. H tilde is A, B, T, C tilde, D tilde, 0. Times, and then we have U transposed, P1 transposed, and P2 transposed. This must be equal to 0. So, and from this we get two conditions. So the first, just looking at the first row, will give that A times U transposed plus B times P1 transposed plus T times P2 transposed is equal to 0. Okay. Now looking at the second row, it means that C tilde times U transposed plus D tilde times P1 transposed is equal to 0. Okay, so from the second line, we can say that P1 transposed is equal to minus sign, let's rearrange the equation, that's minus D tilde inverse times C tilde times U transpose. So we get P1 purely by matrix multiplication of U. So I take U and we multiply U with two matrices, C tilde and D tilde power minus 1. So we have P1. And now what we do is we insert P1 into the first equation. So we insert P1 into the first equation. And then we get that P2 transposed. And of course, we don't need the minus sign if we work with binary numbers. So we can put plus sign over there. So what we get by rearranging the first equation, P2 transposed is minus T inverse times A times U transposed plus B times P1 transposed. Okay, so we can just insert and solve these. Perfect. We can also insert the expression for P1 directly, and that gives us P2 power minus 1, A times U transposed plus B. Actually, it's going to be, let's keep it with all the minus signs. So it's going to be a minus B times D tilde to the power minus 1 or inverse times C tilde times U transposed. And what I can do now is I can just factor out the U transposed. So that means that P2 transposed is equal minus T inverse times A minus B times D tilde inverse times C tilde times U transposed. And again, I can transform all the minus signs into plus signs. So I have also an expression for P2. So the nice thing about this is that because of the row-column permutation, A and B are sparse, T is sparse as well. And only C tilde and D tilde are not sparse, but they are small. These are small matrices because G is very small, so either a very thin matrix or a small square matrix. And we need to invert D tilde. D tilde is also a small matrix, and that's pretty easy. You can just pre-compute and store. You may ask yourself, what about T? We need to invert T. T is potentially a big matrix, but T has a special form. So we know that. Let's take a look at how we can calculate T inverse. So if we look at T, he has this special form of being lower trigonal matrix. So here we have entries and we have 0 over here. So it means we can write T as T11, 0, matrix F, and the matrix T22. And means that T11 is also a lower diagonal matrix, and T22 is also a lower diagonal matrix. So we can subdivide T into a block structure with two lower diagonal matrices, a 0 matrix and some matrix F. So now we can calculate the inverse of T. So the inverse of T is, just write this matrix, T11, 0, F, T22, inverse. And now we can apply something that is called the block inversion lemma. And the block inversion lemma is an expression for the inversion of a block division. So if you subdivide your matrix into such a block structure, the block inversion lemma will give an expression for calculating the inverse as a function of the 4 different components. And because of this 0 here, a lot of these terms in the block inversion lemma will vanish. And what you end up with is the following. So this will be T11 inverse. You will have minus T22 inverse times F times T11 inverse. You have a 0 over here, and you have a T22 inverse. And now, again, you have this, you need to calculate an inverse of T11 and T22. So you can do the same trick because T11 is a lower diagonal matrix. So you just apply the same trick. So what you do then is you calculate T11 inverse. That's equal to T111, F11, 0 and T112 inverse. Again, you apply the block inversion lemma and you get T111 inverse minus T112 inverse times F11 times T111 inverse. Then you have 0 up here and you have T112 inverse on the bottom. And again, you have T111 that you need to invert, which is a lower diagonal matrix. So what you can do is you can just do some divide and conquer. So you reduce your problem of inverting a big lower diagonal matrix to inverting 2 lower diagonal matrices of half the size. And then each of those you subdivide again to get half the size. And you repeat this until you get a matrix of size 2 by 2. And we all know how to invert a matrix of size 2 by 2. Or you even continue until you get a matrix of size 1. Then it's just a reciprocal. So that's actually something that's pretty easy to do. Okay, so to summarize, we have our expressions. So P1 is obtained by this guy. So it's minus D tilde inverse times C tilde times U transposed. And we can get P2. That's given by this expression as we have just calculated. Okay, so essentially that means we have solved this problem, and we can now take a look at what's the complexity of this. So the procedure seems at the first glance quite complex, but if we take a closer look, many intermediate terms, they are actually sparse. So they contain only a few elements. Then we can actually show that the complexity order is n plus g squared. It means if g is very small, we can neglect g and we have a complexity that approaches O of n. The only difficult part is d to the power or d inverse tilde, but it is of size g times g. We have a very small matrix of size g times g. The cost of inverting is g cubed, but we can pre-compute and store this one. So let's take a look at a toy example, but a small example, to see how this method works. So we start with a matrix H. This is our starting matrix. This is just some parity check matrix. And we transform it to H prime by just doing some row and column swapping. And now what we do is we swap the second and the third rows, this one, and then we also swap column 6 and 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We swap these two columns, and then we get the matrix H tilde, or H prime, sorry. To get this matrix H prime, and you see here it has this lower diagonal form. So it has exactly the form that we need for encoding. So this is our T. And we have a G that is 2. Okay, so now what we do is we clear this E. We want to get rid of E. We can either do this by multiplying with this Schur complement, or we can do this using Gaussian elimination. So for instance, in order to get rid of the last line, we just add the first and the third line to the last one. And that means we get rid of the last 101 up here. So adding these columns, so for instance, we'll have row in order to get here. It means that row 5 becomes row 5 plus row 1 plus row 3. And in order to get rid of the fourth row becomes row 4 plus row 1 plus row 2 plus row 3. So just add all the 3 rows together up here, and we see that this will give us 1 plus 1 is equal to 0, and then we have 1, 1. So it will be 0, 1, 1. So that's also how you can get rid of this guy. And of course, these will change. So this will be our C tilde, and this will be our D tilde. Okay, so now we have everything at hand. Now we can do the encoding. So we fix some arbitrary bit vector. So for instance, we fix u to be equal to 11001. X is u, p1, p2. So first we calculate p1. So it's d tilde inverse. And we saw that d tilde was equal to d tilde was equal to 1011. And it turns out that d tilde is exactly the same. It's also 1011. Because if we do this, we have 1 times 1 plus 0 times 1 is equal to 1. 1 times 0 plus 0 times 1 is equal to 0. We have 1 times 1 plus 1 times 1 is equal to 0. And then we have 1 times 0 plus 1 times 1 is equal to 1. So we get the identity matrix. So that's d tilde to the power minus 1. D tilde inverse. This is C tilde. And this is U transpose. And it's just matrix vector multiplication. It's a little bit tedious, but you can calculate it. And you end up with 1, 0 vector. And then we can calculate P2. So we need to invert T. Also something you can try to do for yourself. For instance, using the equation that I just gave. And that's exactly how we did it. Plus A times U plus B times P1 transpose. And that's how you get P2. And P2 is 1, 0, 0. So we have our code word. And actually you can calculate both of these in parallel because by inserting, you could also insert U here. Here we did it by inserting P1 because it saves us some multiplication if you want to do it on pen and paper. And that's essentially how the encoding works. We provide a MATLAB file called Encoding LDPC. And we also provide a file called example encoding and constructing, where you can see how the encoding and constructing of complete code works. There's some word of caution that the encoding we do is not systematic, because that would mean that we would need to reshuffle some of the columns of the original parity check matrix rearrangement, but that's just a small side note. So essentially the procedure, you have it in the examples, and you can try to construct your own code using what we saw in the last chapter, and then do the encoding using what we saw now here. So with this, we have seen the encoding, and in the next video, we're looking at some other code constructions.